Hello students, as we have discussed in the last class regarding the greatest common divisor, now we come to Euclidean algorithm. So here in Euclidean algorithm, we will follow the process of how to define the least, the greatest common divisor of two polynomials fx and gx. So you have here fx and gx be two polynomials with gx different from 0. And here we are considering this fx and gx as two polynomials over the set of rational, real or complex, not over the set of integers. With the condition here, the degree of gx is less than degree of f of x, less than or equal. So here you have, what is this division algorithm, is that by division algorithm here, you divide fx by gx, then there exists divide fx by gx. So by division algorithm theorem, there exists polynomial q1x and r1x such that fx can be expressed in the form of q1x into gx plus r1x, where r1x here is either equal to 0 or degree of r1x is less than degree of g of x. Gx here is called the divisor. Q1x is called the quotient. So if r1x is equal to 0, then we have the common divisor among this is gx, or we can say that, suppose here if r1x is not equal to 0, then what you have to do is you divide this gx. The process of division algorithm is that you divide this divisor by the remainder, divide gx now by r1x, and again by division algorithm there exists unique polynomial q2x and r2x such that this one gx can be expressed. The divisor here is r1x, so r1x, the quotient is q2x, and then plus r2x, again where r2x here is equal to 0 or degree of r2x is less than degree of the divisor here is r1x. This process will continue. For a finite number of steps till you get the least remainder, say rk plus 1, means suppose here r2x is not equal to 0, r2x is not equal to 0, then you divide this polynomial r1x, divide r1x by r2x. So again by division algorithm there exists q3x and r3x such that this one r1x can be expressed as q3x, the quotient polynomial, into the divisor, that is r2x plus r3x, again where r3x here is equal to 0 or degree of r3x is less than degree of r1 or r2x. So this process will continue for a finite number of steps. To get the least remainder, say rk, process will continue for a finite number of steps to get the least remainder, say rk plus 1 of x is equal to 0. So with this we thus have the following process of division algorithm, where f1x you are given polynomial f1x and divided by gx, so there exists by division algorithm q1x plus r1x, where degree of r1x is less than degree of g of x. Now if r1x is not equal to 0, so you divide gx, this gx by r1x, so you have R1x here. So there exists quotient polynomial Q2x plus the remainder R2x, where degree of R2x is less than degree of R1x. Again, if R2x is not equal to 0, so you have here, you divide R1x. So R1x here is equal to Q3x into R2x plus R3x, where degree of R3x is less than degree of R2x. Dash dash till you get RK minus 1x is equal to QK plus 1x into RKX. QK plus 1x into RKX, because RK plus 1, since these steps will continue for a finite number of, this process will continue for a finite number of steps to get the least remainder RK plus 1 0. So the last non-zero remainder here, that is RK plus x, is called the greatest. Here this is not this RKX is the least non-zero remainder, and it is the GCD. It is the GCD of f of x and g of x. So what is this division Euclidean algorithm? You are given two polynomials fx and gx with gx different from 0. You divide fx by gx. What you get is there exists by division algorithm, there exists quotient polynomial q1x and r1x such that fx can be expressed in this form. If r1, where r1x equals 0 or degree of r1x is less than this. Now if this remainder r1x is not equal to 0, you divide gx by r1x. But again, using division algorithm, there exists quotient polynomial q2x and r2x such that gx is equal to q2x into r1x plus r2x, where r2x equal to 0 or again degree of r2x is less than degree of r1x. Now if r2x is if r2x, this one, is not equal to 0, you divide r1x by r2x. By division algorithm, there exists quotient polynomial q3x and r3x such that r1x can be expressed as q3x into r2x plus r3x, where r3x is equal to 0 or degree of r3x is less than degree of r2x. So this process of division of polynomials will continue for a finite number of steps till you get the last or the least non-zero remainder, till you get the remainder, say rk plus 1x is equal to 0. And we thus have the process here of using this division algorithm here is that first you divide fx by gx. What exists here is that q1x and r1x. Now if r1x is not equal to 0, you divide gx by rx, so there exists q2 and r2. If r2 is not equal to, so we thus have this process fx here, when you divide it by gx, so there exists q1x and r1x. If r1x is not equal to 0, you divide gx by r1x, so there exists q2x and r2x. Again, if r2x is not equal to 0, so you divide r1x by r2x, so there exists quotient polynomial q3x and r3x remainder such that this process will continue for a finite number of steps till you get the last non-zero remainder here, because this process will continue till you get rk plus 1x is equal to 0. So therefore the last one, since rk plus 1x equals 0, you have rk minus 1x is equal to qk plus 1x into rkx plus rk plus 1x, but rk plus 1x here is equal to 0, so it will stop here. So this rk of x, that is the least non-zero, this is the smallest non-zero remainder you obtain, will be called the greatest common divisor of these polynomials fx and gx. So here, as you can see, this is r1x, you have here r2x, r3x. So last step will be rk minus 1, so it will be qk plus 1 into rk, as you can see q3, r2 and r1. So here if you have rk minus 1, it will be k plus 1, 2 times greater than this one, and r2 here it should be rk. Okay. So I hope it is clear, and this process of division of polynomials to get the least non-zero remainder is called Euclidean algorithm theorem, Euclidean algorithm process.